ได้ไหมครับอาจารย์
โอเคโอเคเอ๊ะมันหลุดไป
ขอบคุณค่ะ
ได้ด้วยเหรอ13 minutes record เอ๊ะthere's something strange มีใครบางคนไป ปิด record มาหรือเปล่า okay so now I'm recording. Okay, so if there's something wrong with the files or with the MS Teams, you can just inform me. So sometimes I'm not with the MS Team screen, so maybe there might be something wrong. You can tell me immediately. Otherwise, we cannot fix the problems in time because the time is already gone. Okay, so the next issues which are related to the uh, intake facilities is the pumping system. So for the pumping system, actually it is the part of the chapter 4, but I have taken this part out from the chapter 4 and make it separate sections. So these presentations, you can also get it from the files. You can get this presentation from the files here in general, and in class materials you'll find two separate presentations related to the chapter 4, which are the pumping system. I will use this file for the lectures, for the today's lectures, and the another one is the heady clause. This is also one part of the chapter 4. So for the pumping system, yeah, of course, we all know that the pumps is one of the most important component used in both water and wastewater treatment plants. Talking about the pumping systems, the pumps itself, we can actually classify into two major types. One is the kinetic energy pumps, which include the one which is widely used. I'm sure that you also have at home. The one which we normally use is the centrifugal pumps. These centrifugal pumps we use for various purposes. Sometimes we use to transfer the water from the lower elevations to the upper elevations, or sometimes we use these kind of pumps to increase the pressure in the piping system in our house. The pressures that we typically use should be around 2 bars. 2 bars. Bars is the precious unit. I hope you still remember. 1 bar is equivalent to the water column's height, 10 meters. So 2 bars, it means that 20 meters, equivalent to the water column's height. But talking about the mercury, so it's 76 centimeters. So hopefully you can still remember these uh, comparisons. So we normally use the centrifugal pumps to supply the waters in our house and many other places. The farmers, they also use these types of pumps to withdraw the water from the surface water or any other water resources into the fields, the paddy fields, or the agriculture areas. Uh, other these types of pumps, so we acquire the energies from the electric cities. Then we are the motors, and for the motors, the energy is transferred to the impellers, and then in the casings equipped with the impellers, so the pressures can actually be raised to lift the water from the lowest elevations to the upper elevations. So centrifugal pumps is probably one of the most widely used for various purposes. Other pumps which belong to these groups, for example, the peripherals or the vortex pumps, rotary. So these are also a kind of kinetic energy pumps. So you will see the photographs in the next slide. And the second types of the pumps is the positive displacement pumps. Sometimes we also use this kind of pumps, for example, in supplying the chemicals to the treatment plants, supplying like alums or the chlorines into the clear wells or the coagulation flocculation process. We sometimes use this kind of pumps, especially the diaphragm pumps. So the pumps which belongs to these groups of, for example, diaphragms, screw injector, pneumatic injectors, puncture, or airlift. Here is the descriptions for various types of pumps. Centrifugal pumps, basically impellers, rotated inside, and in closest casings, the head is developed by the centrifugal force created by the impellers rotation. Head or pressures are related to each other. So if we are talking about the head, the unit is water column's height. We normally report it in terms of meters or feet. But talking about the pressure is the forces acting on the areas. So normally the pressures, we define it as the Newton per square meters. The magnitude of the force is always expressed in terms of newtons, acting on the areas, square meters. So the unit is newtons per square meters. But anyway, the head and pressures are both related with each other. For the pressures, if we divide it by the specific gravities of gamma, P divided by gamma. So this will be the head. I hope you can still remember the basics fluids are fundamental knowledge. The diaphragms similar to the piston. So the pistons are is something like there is a cylinder inside, there is a pistons. So the pistons oscillated and displaced the amounts of the fluids which each stroke. So let's have a look at the photographs how it works. This is the photographs of the pictures of the centrifugal pumps. So basically, you see the pumps consist of many parts. The major parts of the centrifugal pumps are basically the motors. It's here. The motor we use to drive the impellers. So impellers is installed inside the casings. So if we cut these sections, you find something like this. So in these pictures, here is the impellers. This one is the impellers, and this is a casings. So impeller is installed inside the casings. So water enter to the casings at the in the axial directions, and due to the centrifugal force, the liquids it's pushed to distribute and then touch the walls of the casings. So this process can actually increase the pressures or the heat to the liquids, so that the liquids can actually move up this is why the liquids can be lifted from the lower elevations to the upper elevations. The designs of the centrifugal pumps, you see, this is the impellers with the round shaped. Then the distance measuring from the edge of the impellers to the casing wall. This one is this location is very small, and then gradually increased with the constant increasing rate. So the ratio between this distance with respect to the to the casings areas are basically constants. As you can see from these 3D pictures, the fluids it's entering to the axial directions, and these impellers actually rotated so that the water can actually discharge it into the other directions. So this is how the centrifugal pumps work. Other types of the pumps that sometimes we used is this one, the jet pumps. The pressures with the high fluid is injected here. So these high fluids liquids actually can induce the waters or the fluids to get inside before discharging to the other side. So this is what we so call the jet pumps. Anyway, these pumps needs the high pressure fluids injections. The high pressure fluid injection actually it's also the water. So we have to push the water through this small vortex, so that due to the high velocities, this jet can actually induce the waters of the fluids from the other directions and get into the pumps. Centrifugal pumps by the concepts, so it's made or operated principally by the centrifugal force, and the inlets to the pumps. So water it's entered to the pumps casings in the axial directions, and then the outlets it in the tangential directions. And then, okay, so the assignments is already distributed. Today's assignments is already distributed, so you can check it later. So the assignments will cover the storage volumes determinations and also the pumping system. So at the end of the class, you can do these assignments. The flow is accelerated by the rotating impeller. As I mentioned, radials and tangential, which imparts to both the radials and tangential velocities. This ratio depends on how the mechanical engineers designs the impellers. The cross sections of the volute or the casings produced the change from the velocity head to the pressure head. Okay, velocity head is given as the v squared divided by 2g, and the pressure head is always given as the p divided by gamma. Gamma it's the specific gravity. This one is the photographs of the pictures of the positive displacement pumps. There are two types of pumps shown here. The diaphragm pumps. This one is the diaphragm pumps. This one is the peristaltic pumps. For the diaphragms, there's a punctures here. So when the punctures moved to this side, so the diaphragms it's also punched to the other side. So water can actually get into this chamber, and then once it push back, so water can get out from this chamber. So this is how the diaphragm works. So these pumps can actually locate it just next to the reservoir, or maybe besides the water tanks. But for the peristaltic pumps, here is the tube. Normally we use the silicone tubes, and this tube is equipped inside this we normally call a pump head. Here there is the shaft that are always rotating, and the pipes it's actually pushed inside this water head. So once this one move or rotated, water can actually get inside and move into this tube. So based on the water replacement concepts. So water can actually transfer from this side to the other side, depends on the directions of rotations. So if it's rotated in the clockwise directions, water can actually move from the left side to the right side. But if it rotates in the counterclockwise direction, so we can transfer the waters from this side to this side. So these pumps sometimes we use in the plant just to supplying the chemicals. This is very small pumps. We don't use to carry large volumes of water. For the large volumes of waters, it is recommended to use the centrifugal pumps, not the positive displacement pumps. This one is the rotary pumps. Just a moment. I think I have some other photographs. Okay, so this is the rotary pumps. This pictures may be a little bit complicated, but if you really look at this pumps, at this pictures, you will see something easier. So water just get into this chamber. This is the chambers where we used to transfer the water from this side to the outlet. And then here there's a rotor. Rotor it's always attached with the wall of the casing. So once it moves like this, so water can actually get into inside this chamber. But once it moves in further, so water can actually push it so that it can get from the get out from this chamber where this outlet. So this is how the rotary pumps work. So there's a blade here equipped with the springs. These equipments will have the rotors to move attached to the walls of the casings. For the pumps in the water treatment plants, we used various types of pumps. This is probably the flow diagrams of the water treatment plant. Raw water gets into the intake systems, and then there is raw water pumping stations, and after that we have the rapid mixing tank just to add alums to coagulate the colloidal particle, followed by the flocculation process. So after flocculations, there may be the sedimentations and then filtrations. Once the water passed through the filters, the treated water is kept inside the clear water storage. In here, we may apply the chlorine, and after that the waters it's again uh, uh, distributed to the community where they are serviced pumping stations. So at each unit, various types of pumps can be used. For example, the raw water pumping stations, we can use the centrifugal pumps. But for the chemical handling, chemical stations, mostly we use the diaphragm pumps, or sometimes we use the screw pumps or the rotary pumps. So mostly we use the positive displacement pumps for the small volumes uh, uh, liquids transportations. But for the sedimentation tanks, normally water overflow from these tanks to the next unit operations. But we have to handle the sludge, which normally accumulated at the bottoms of the chamber. So in that case, the sludge, once accumulated, we have to pumps, we have to transfer them to the sludge treatment facilities. In that case, we may use the peripheral pumps, or we may use the piston pumps, because the liquids containing the sludge is quite sticky. The viscosity is a little bit higher than the uh, normal water. That is why we need the pumps which with the powerful power to transfer these liquids into the sludge treatment facilities, like thickeners or the sludge dewatering. Talking about the pumping stations, we can actually classify it into two types: wet well and dry well. So how does it look? For the wet well, normally the pumps is hanging or submerged, or the pumps itself actually live. Uh, we keep it inside the well, and then once it in operation, the water gets through these pumps directly, and then we transfer this to the next unit operations. But for the dry well, the pumps is just located next to the tanks like this. So we uh, withdraw the waters from this wet well tanks, and then supplying this water to the coagulations and floculations and so on. So this is the wet pits and dry pits pumping stations. And for the installations of the pumps, especially for the centrifugal pumps, we can say that there are two types of the pumps installations. So the first one, the centralized of the pumps is above the water levels in the suction reservoir, or in between the water levels in the lower reservoir and the water levels in the upper reservoir, as it shows in these figures. And then the second case is the centralized of the pumps. So when I'm saying about the center line, so it means this line, the horizontal lines lining on the center of the impellers. So the second types, the center lines of the pumps is below the water levels in the suction reservoir. So as you can see it in figure B. So the difference between these two installations is in a figure A, so it's more or less the lift suctions. But in a figure B, so it's the flat suction. So flat suction, what does it mean? It means that the waters can actually pass through the pumps due to its levels higher than the center lines of the pumps. The discharge reservoir or the upper reservoir is located in the higher elevations. So these two types of installations, if I'm asking which one is better, so the one which provided the better suction performance is the installation as shown in a figure B. B is better in terms of the suction's performance. But anyway, there are some terms which we can learn it from these two figures. So water difference, the difference between the waters in the lowest reservoirs, water levels in the water reservoirs, and the water levels in the upper reservoir. So the difference in terms of this water levels, we typically call the total static head. We normally call the total static head. A static means the pumps is still not in operation. Is the impeller is not moving. So for this difference, we normally call the total static head. And for the difference between the vertical distance between the center lines of the pumps and water levels in the lower reservoir, this is actually divided as the static suction head. This one is the static suction head. So the pumps has to lift this water from the lower elevations and the water will be transported into the pumps which located above the water levels. And the last one, the vertical distance between the center lines of the pumps and the water levels in the discharge reservoir. This is actually divided as the static discharge head. The same concepts if you really look into figure B. So water levels difference is still divided as the total static head. And for the static suction head, it's also still divided as water levels in the suction reservoir with respect to the center lines of the pumps which located in the lower elevations. And the center lines of the pumps, from the center lines of the pumps to the water levels in the discharge reservoir, this we normally call the static discharge head. So there are two cases of installations. The first case, the relationships shows that the total static head is equal to the static suction head plus the static discharge head. So this one is equal to this one plus this one. But for the second figures, the relationships is different as compared to the first case. So for this case, you will find the static discharge head is equal to the total static head plus the static suction head. So suction plus the totals will be equal to the static discharge head. So these are something difference between these two figures. The common hydraulic terms and definitions which we normally used in the design of the pumping system or the pumping stations are mainly consists of these three terms: the head, capacities, work power, and efficiencies. The capacity in this context means the flow rate, but the head refers to the water column's height, which normally divided as the meters. That is the unit of the head. So remember that head is equal to P divided by gamma, or the specific gravity. So this is the difference in terms of the pressures and head. So you can actually have a look. So the pressure uh, uh, we uh, we normally use the head instead of the pressure because the pressure may change if the specific gravities of liquids is changed. Specific gravities actually vary depending on the temperature. So the higher temperatures will be one specific gravities, and then the lower temperatures will be another specific gravities. I'm not sure. Have you ever noticed? We always talk about the densities of water or specific gravities of water. We normally say like water. Uh, the weight is approximately 1 kilometers if you bring waters 1 liters. So 1 liters of water is equivalent to 1 kilograms. That one is the specific gravities, or actually that is the density, but it's also the same as the specific gravities. So this amount can be changed sometimes, vary depending on the temperatures. But if you divide it by gamma, so everything is uh, gone. I mean, the problems with regard to the pressure is gone. So better we expressed the head into. We normally use the head, and then the head is normally expresses in terms of water columns height, meters, feet, and so on. Uh, this one is the different types of the pump heads, and with the definition. The static head is the total head when the pump is not running or not in operation. So mostly the static head refers to the height. The second one is the total dynamic head. Total dynamic head, it's also the head, but the head which generated during pumping, or when the pumps is running. We call the head during in operation as the dynamic head. The total dynamic head, it's actually equal to the static head plus the loss. The head required for the pumps, we have to combine the static head and then the head loss, because loss is may generated due to the frictions in all types of the pipes, all types of the water conveyance systems. Water conveyance types, they basically consist of the sum of the head loss, the pipe war generate the head loss, and the head loss due to the friction. We normally recognize this loss as the major loss, and the loss due to the uh, uh, connections, piping systems, and so on. This loss is normally recognized as the minor loss. So we have major loss and the minor loss. For the major loss, you may familiar with the Darcy-Weisbach equations. So we apply this equation to determine the loss. But in water supply engineering work, mostly the liquids we are dealing with is the water. Water is quite clean. The viscosity is not very high. So uh, it is more, it is much better to use the equation called the Harsens-Williams equation to determine the head loss. So if the liquid is water. So in water supply engineering, we normally use the Parsons-Williams equation. We rarely use the Darcy-Weisbach equation. Darcy-Weisbach may be very useful for some specific purposes, but not for water. So for water, it is better to use the Parsons-Williams equation. And what are the difference between the Parsons-Williams equations and the Darcy-Weisbach equations? What are the major difference? So Darcy-Weisbach, I think you are familiar and know each terms in this equation. So F is the friction factor F, L is the length. So the longer length will be the higher head loss. The velocity, it also depends on the diameters, but for the diameters, the smaller will be the higher. The smaller the pipe diameters will be the largest the head loss, or according to the Darcy-Weisbach equations. But for the Parsons-Williams, V is still the velocities. L is still the length. D is still the diameters. And the last one is the C. So what is C? So in Darcy-Weisbach equation, we have F. F is the friction factor. But C in this equation is also the roughness coefficients. But this roughness coefficient is fixed. Okay, it's fixed depending on the types of the materials used to make the pipe. And the other thing which makes these two equation difference is the this one is V to the power of 1.85, but the earlier equation V square. So this one is V to the power of 1.85. This one is V to the power of 2. So these are difference between the Parsons-Williams equations and the Darcy-Weisbach equations. For the Parsons-Williams equations, normally we use for the waters in a force main. The velocities can be determined from the previous equation. This is the previous equations. This is the Parsons-Williams equations. From here, from this equation, we can rearrange these equations and express in terms of V, and sometimes express in terms of Q. For the SI unit, V is equal to 0.355 CD to the power of 0.67 loss divided by length to the power of 0.54. But if we multiply the V by Q, so Q is equal to AV, right? So if we multiply V by the areas, so we'll get this values Q'd. So what is the areas for the cylindrical pipe, for the round pipe? So what is the areas for the round pipes, cross-sectional areas of the round pipe? So it's pi d squared divided by 4, right? So it's pi d squared divided by 4. That is why the coefficients in the fronts of these equations are somehow different. So many times I always say, like, be careful about the unit because some of the equation that you use are basically the empirical formulas. So if it's the empirical formulas, the unit may not be corresponding with each other. So the better way is trying to apply this directly or sorry. Okay, so now Q is equal to AV. So pi d squared divided by 4, you get this equation in terms of the SI unit. For the Parsons-Williams friction coefficient C, for example, it depends on the types of the pipe, materials made for the pipe, smooth and straight cast iron. The new one, C is 140. But if it's getting older, more frictions in the pipe wall, so that the Parsons-Williams coefficient C it's getting lower or reduced. For the concrete or the cement line, the C is 120. A plastic, the wall it's smoother, so that the C it's 150. At Desktop cement, it's in between 120 to 240. So you can apply these Parsons-Williams coefficients and pick the coefficients and substitute into this equation. So it's simple, but if you use the Darcy's Weisbach equation, you have to determine the friction factor F, which you have to you have to look into all the Moody's diagrams, and the Moody's diagram is also not very simple. First, you have to determine the Reynolds number, and once you know the Reynolds number, you have to check the epsilons divided by d, but sometimes the velocities are vary, so you have to determine the Reynolds number one by one, and in order to get the friction factor F. So this is a kind of complications if you use this kind of equations. Just a moment. Sorry, there's the answer, Gen Core. Okay. Here is the information you have to use for the Darcy-Weisbach equations. But if you use the Parsons-Williams equation, so it will be very simple. And for the minor loss computation, minor loss is equal to K V squared divided by 2G. So you can apply the K values. The K values can be obtained from this table. minor loss coefficients k. For the axis, you have to take k1, but for the globe valve fully opens, it's quite high at 10. The square entrance is just 0.5. So it depends on the types of the connections in the piping system. So you have to apply this one to determine the uh, the uh, uh, the minor loss. Okay, so basically, we need to see the TDS once the pump is in operation. So we have to check the total dynamic head. The total dynamic head sometimes we call the system head, total system head. Sometimes we call the HQ curved. So it depends on the flow rates. So the total dynamic head actually vary depending on the flow rates. So the static head is constant. Static head is basically constant, but the major loss and minor loss vary depending on the flow rates. The flow rates. Okay. Uh, Actually, the velocities, but as Q is equal to AV, V is equal to Q divided by A. Okay, so we can say that the major loss and minor loss vary depending on the flow rates. So if you plot the curve like this, so if you plot the curve like this, x-axis is the flow rates and y-axis is the TDS. So how the curve will look like? So if we don't concerns about the static head, we only focus on the major loss and minor loss. So at the 0Q, the loss is also cannot be accounted. But if we increased the flow rates passing through the piping systems, the loss will increased like this, because this is the square, and this one is the exponential to the power of 1.85. So it will be something like this. If we plot like the TDH versus the flow rates, we just ignore the static head. But if we put the static head combined with the major loss and minor loss, so you will get the curve something like this. So this one is the static head. This one is the static head. So if the pump is not in operation, the water levels, the difference in terms of the water levels in the lower reservoir and then the higher reservoir, this one is the static head. Okay, so this is the fixed. Initially, it's equal to the water level difference. But if we increase the flow rates, the head loss will increase accordingly. Okay, normally it is like this. I mean, if you want to plot the curve, so this curve sometimes we call the HQ curve. This one is the head and this one is the flow rates. Or sometimes the people may call the system head curve. Or sometimes people may call like a TDH curve. Depends on the reference. This curve is very important whenever you want to select the pumps. Okay, we need to establish this curve before selecting the pumps. Okay, so this is the Parsons-Williams equation. Now, if you are about to establish the curve, so how we can do that? This is the example, but unfortunately, they used the Darcy-Weisbach equation. This is the systems. So the reservoir, the pumps is just transfer the water from this reservoir to the other reservoir located on the other side. But there is no water levels difference. Probably just increase the pressure. By the way, this one there is no static head because water levels are equal. So if you want to determine the HQ curve, the HQ curve, it's actually look like this. System head curve actually look like this. So it's equal to the major loss plus the minor loss. So what you can do is you have to determine the minor loss. Minor loss, it's K V squared divided by 2G. So if we have the entrance and also if we have the exit, so you have to look into the K value. You have to check the K values, which we obtained from this table. And then determine for the major loss. Major loss is according to the Darcy-Weisbach equation. So F L divided by D, V squared divided by 2G. So combinations of all major and minor. So you get the relationship between the TDS and the flow rates. Okay, but the problem with this equation is that you have to determine the friction factors because according to the Moody's diagram, the friction factors vary depending on the Reynolds number, and the Reynolds number vary depending on the velocities. So can you see the velocities here? So as it vary depending on the velocities, so once we change the flow rates, then the velocities through the pipes is also changed. So we have to divide it one by one, case by case. So it's very complicated if you apply this equation. That is why you have to, so this is the TDS expression in terms of the Q. And this one is the Reynolds number expressed in terms of the Q. So we have to determine the friction factors. So once we get the friction factors, we can determine for the TDS and the flow rates that we assumed initially, we put it in the x-axis. And then for the TDS at each flow rates, we determine from the relationships or the equations. So at the end, we will get the curve look something like this. So this is the curve that we obtained from the Darcy-Weisbach equation, which is a little bit complicated. Another example, also the same. They use the Darcy-Weisbach equations, the combinations of all the lost, minor loss and the major loss. So according to these figures, the pumps it's actually suck this water from the lower reservoir. The water levels is located at the elevation plus 14 meters above the mean sea levels. So we have to transfer these waters into the upper reservoir with the water elevations of about plus 35 meters. So static head in this case is equal to 35 minus 14, 21. It's 21. And there's the details about the pipe. The pipe diameters 6 meters, 5 meters in this for these sections, 20 meters for these sections, 15 meters, 40 meters. There's a check valve here. Why we need to use the check valve? Check valve will actually help to prevent the liquids moving back into the lower reservoirs again or into the suction pipes again. So this will help to prevent the moving water moving back to the suctions pipe. Our system is something like this, and then we need to determine for the minor loss and the major loss and explain all the TDH in terms of the friction factors and then the Q. Okay, so this one is the loss combination of the major and minor loss. And if we combine it with the 21, 21 is the static suction head. Then determine for the Reynolds number. Finally, we get the flow rate. Flow rate we have to assume. So if we are interested in the flow rate ranking from 0 to 0.2 cubic meters per second, so you just vary the flow rates in between, and then determine for the TDH. And according to this TDH, you can establish this curve, the system head curve, look something like this. So the system head curve actually vary depending on the system. So if you change the system, the TDH curve patterns will change accordingly. So it depends on the system. So if you shorten this pipe, maybe the minor loss or the major loss can be minimized. So it depends on the system. So each system has its own the TDH curve or the HQ curve. Okay, so HQ curve we have to establish. So it depends on how we install the pumps and how we install the pipes. It depends on the distance. It depends on the elevations, water levels different. And if we want to select the pumps corresponding with this installation, so how we can do that? That is the problems. So the major points of this aspect of this topic is so how we can select the pumps appropriated for our system. So in this case, what we can do it? We can do it like this. This is the curve showing the total dynamic heads and at various discharges. So this is the HQ curve. Okay, this is the HQ curve. So we have to establish this curve. So this curve, remember that this curve vary depending on the system. So different system, different curve pattern, but it's an exponential curve like this. So it looks like a conventional exponential curve. So according to this one, this is our system. But if we want to select the pumps, so whenever we talk about the pumps, our situation is like this. So if we want the water transporting from a lower reservoir to the upper reservoir, and our system is like this. So if we want the discharge at 0.3 cubic meters per second, and we want the total dynamic head at least a 40, so we need the to operate the pump above this point. Okay, so if the head we want above 60, so 60 may be the static head combined with the lost due to the frictions and then the minor loss. So if you want to determine the pumps which corresponding with this condition, so how we can select or how we can use that, how we can choose the pumps. We are talking about the buying a new pumps which meet our requirement. So this is our requirement, system requirement. So if you want to buy the pumps, if you go to the pumps vendor shops, they will show you something like this. They will offer you a pump curve like this. This is actually the pump curves provided by the pumps manufacturer. So there are so many lines, and some looks similar to the control lines. But just think about the pumps itself. Just think about the pumps itself. So the capacities of the pumps is something like this. So if you just think about the pumps, so the pumps is actually carry the water from the lower reservoir to the upper reservoir. Okay, so this is the upper reservoir. This is the pumps. Okay, these pumps, just think about the capacities of the pumps. So for the pumps, not the systems, okay, for the pumps, just think about the pumps. So the pumps, so if we want the pumps, if we want to pump that water from lower reservoir to the upper reservoir, if we want the larger flow rates, if we want the larger flow rates, you cannot keep water levels difference higher. Okay, total head. I'm talking about the total head uh, that the pumps can actually carry the water, and with respect to the flow rates the pumps can carry. So for the pumps, if you want the large flows, you cannot pump uh, too high, too large in terms of the water levels difference. Okay, so at uh, the relationships between the uh, total heat carried out by the pumps with the flow rates, it's given like this. Uh, if you want to pump the water with the higher flow rates, you cannot pump uh, at a very high water levels difference. But if you want to pump from very low elevation to a very high elevations, you will get very small flow rates. But if you pump from lower elevations to the higher elevations like this, the difference is not so much. You will get a larger flow rates. This is the capacities of the pumps. It will always work like this, especially for the centrifugal pumps. So if you need the large flow rates, the water level difference shouldn't be too high, too large. But if you want to pump from a very low elevation to a very high elevation, you will get only small flow rates. So this is how the centrifugal pumps work. We are talking the pumping capacities. We are not talking about the systems, okay? This is the capacities of the pumps. So they can actually carry the flow rates, but at some certain head. So if you want to pump uh, uh, with the larger head, then you only get the small flow rate, okay? The thing is, the manufacturer, they provide a series of the pumps curve for you. This is one pumps, and this one is another pumps. This one is another pump. This one is also another pumps. Each pumps has different capacities. This one, the power is 7 horsepower. So this is a little bit bigger, 7.5. This is 8 horsepower. This one is slightly bigger, 8.25. So this is the pumping size. This one seems to be a smallest. This one seems to be the largest in this series. So there are 4 different types of the pumps. Okay, so according to the manufacturers, if we want to select the pumps uh, corresponding with our system. So suppose our systems is something like this. So if we look at it, if we bring the HQ curve and put the HQ curve onto this pump curve. So you will find something like this. This is the line HQ curve, or the TDH curve. The thing is, the intersection between the pump curve, this one is the pump curve, this one is the HQ curve. So intersection between the pump curve and the HQ curve is the point where the pumps work. What does it mean? It means that if you choose 7 HP, so if you choose this one, so it can actually deliver the flow up to these values only. This may be 180 maybe, and then the flow rate will and then the head would be around 32. But if you choose 7.5, you will get larger flow rate and also the higher head. If you select this one, you will also get the larger flow rates and also a little bit higher head. It depends on the flow rates we required. So if we required 120, so if we required 120 and the head it's approximately 40. So this is 40. And our system's head curve is here. So this one is the 120. So in this case, we need to choose the pumps with the inputted power, required inputted power 8 horsepower. So we have to choose this one. This one will not meet our requirement. 7 and 7.5 are both do not meet our requirement. So we have to choose the larger one. And what about this one, 8.25? 8.25 it's also work, but also can work, but see the larger pumping capacities will be very costly. So as the engineer, we are trying to avoid any unexpected costs for the constructions for the operation. So it's not just the budgets, but it's operations and maintenance cost we have to spend if we use the larger one, which is not necessary. But anyway, if you use the larger ones, if you don't have the budget problems, if you use the larger one, like if you use 8.25, 8.25 actually we will get the better or the larger flow rates. We get the larger flow rates. I mean, the larger than what we want. And also we get the higher total dynamic head. This is actually better in terms of the capacities. But if we don't have any problems about the budget, you may choose the big one. Why? Because the big one is not just it meet both flow rates and then and the total heat required, but it also gives the better efficiency. The lines with the curve, so many lines, curving lines like this. This shows the efficiencies of the pumps. So the pumps has various efficiency depends on the conditions they work. If you choose this one, if you choose like for example the 7, this is the smallest one. The efficiency this is the working conditions. The efficiency will be only 55%. If you choose the bigger one, the efficiency will be like a 63 or 64%. But if you choose this one, it actually meets our requirement, and it also gives the better efficiencies. But if you choose the biggest one in this pump curve, you get above 70%. But now as the engineers, we have to compare, you will go whether you go for this one or you will go for this one. Our efficiency, what are this efficiency? What does it really means by the efficiency? The efficiency is like this. Actually, the efficiencies, we compare the power. When we talk about the efficiencies, it means that we compare about the power input and the power output. The one which we require for the system, it's the power. It's called the power output. The power output required for the systems it's equal to, so actually it's equal to P equal to gamma QH. We can simply write like this. Gamma is the specific weight of the liquid, so it normally expressed in terms of kilonewtons per square meters. Q, it's definitely flow rates or the capacity for the SI unit. Q, it's cubic meters per second. This is not the empirical formulas, okay? This is the homogeneous equation. So unit must be corresponding with each other. So if you use SR unit, Q must be expressed in terms of cubic meters per second. If you use the TDS, if you want to substitute the TDS, the unit must be expressed in terms of the meters. If you want to use this one, the unit that you need to substitute, the value that you need to substitute, the unit must be a Newton per square meters. But if you substitute by kilonewtons, so the power will be expressed in terms of kilowatts. But if this one is a kilonewton, but if it's just Newton, so the power determined from these relationships will be also expressed in terms of watt only. So H is the TDS. So that is why I'm saying what flow rate you want at, and also at what the total dynamic case we want. So we chose the pumps, and based on the pumps that we chose, so what will be the power output from that pumps we selected. So this is we can estimate the power output of the pumps. So power output of the pumps can be determined from these relationships. So it normally expressed in terms of kilowatts. So if it's kilonewton, the power output, you will get in terms of kilowatt. But anyway, it doesn't mean that, okay, the power output is obtained from this relationship. But whenever we think about the power input, so we have to input some more, because some certain powers will be lost. Some of the energies will be lost. So normally powered output divided by powered input multiplied by 100%. This will be the efficiencies of the pumps. So when we talk about 70%, so it means that power output is only 70% with respect to the power input. Okay, but in fact, the systems will actually acquire the power from the electricity transferred to the motor, and then from the motors, the energy it's sent to the pump itself. So pumps here means the impellers plus casing. In this slides, the methods for the determinations of the efficiency it's a little bit more complicated. Okay, uh, uh, from the motors, efficiencies of the motors are when we pass the electricity to the motor, there is a loss, and again from the motors to the pumps, there is another loss. But anyway, for the motors, normally the motor's efficiency is quite high. It's actually near the 100%. But from the motors to the pumps, the energies or the efficiencies is actually vary from the 60% to 85%, like I showed you in the previous slide. So some references that just ignore the motor efficiencies. So just take the power input output divided by power input into 100%. So this will be the power input. Okay, so these two will be the powered input. That is why in the previous curve we get the number like a 70%, 60%, and minimum would be like a 55%. So this is how we can determine the power and how the power is related with the efficiencies. As I mentioned, so if we have two choices, so which one we would go for? 8, it's also okay. 825, it's also perfect. So which one we would go for? So if we have two choices, so if both can actually carry out the sufficient flow rate we want and at the elevations or the height we want, then we have to look for another criteria. So if it's already meet that two criteria, so we have to look for another criteria. Another criteria is the efficiency. So if the efficiencies we get it from the pumps is actually high enough, like 60 to 70% and above, that would we will pick that one, the one which give the maximum efficiencies. So if we have, in case if we have two choices. But anyway, this is just the procedures to select the pumps in hydraulic labs. Unfortunately, this semester you are not doing you don't have a chance to work in the hydraulic labs. In the labs, there is one experiment called the pumping system. There is an experiment you have to establish the pump curve. You have to establish the curve like this in the labs, from the labs, and the results that you obtain you will find the curve will look something like this. You have to find you have to establish the curve based on the information collected from the labs. I remember because previously I was the one who in charge with this lab. So students are asked to prepare the pump curve, one pumps in operation. That is the first condition, and the second condition would be two pumps connected in series and two pumps connected in a parallel. So how the pumps curve will look like. So that is what you have to measure from the lab. Okay, so I just want to summarize again. So if you want to select the pumps, you have to follow this instruction. First, you need to establish the total dynamic or the system head curve. Then you put this system head curve onto the pump curve. The intersection between the pump curves and the system head curve is the point where the pumps will be working. And the intersection should actually located on uh, uh, the conditions where it gives the highest efficiencies. So that is the ideal conditions. So it actually meet the requirement and the efficiency should reach the highest. That is the ideal conditions. Or may slightly drop it, that is acceptable, but not very low, like a 50% or smaller than 60%. Okay, so this is how we select the pumps, how we chose the pumps. There are some other conditions. Sometimes we cannot choose any of the pumps from the manufacturer. In that case, what we can do, it is possible that we don't get the pumps from manufacturers. Sometimes we need to take two pumps connected in series. Sometimes we need to take two pumps connected in parallels. So what does it mean by the two pumps connected in series or in parallel? In parallel, it's something like this. So we have the suction reservoir. So this is the pumps supplying waters to the upper reservoir. So this is just one pump. So if we have like a pump number 2 and pump number 3 connected like this, so this one we normally call three pumps in uh, parallel. Okay, so this is we call the three pumps in parallel. The beneficial use for connecting three pumps in parallel is that you can get the higher flow rates, but the loss will be the same. Okay, but sometimes if you want to carry the waters from the lower elevations to the upper elevations, the pumps that are available in the company, in the pumps vendor, still does not meet our requirement. Sometimes you may have to buy two pumps and connect it in series like this. So connections of the two pumps in series like this will be beneficial in terms of the head. So you will achieve the higher head once you connect two pumps in series. But for the flow rates, if you need a higher flow rates, but other things remain the same, you may connect the pumps by one or two more pumps and connect it in series like this. Okay, so this is how we arrange the pumping system in both water treatment plants and some other places. Okay, so this is what I'm talking about. Just look at this example. I think it's almost the last, second to the last slide. In this example, this is our system head curve. I just highlighted by the yellow line. We have two pumps. We have two options. The first option is pump A. Pump A has the characteristic like this. This is pump A. And pump B actually has the characteristic like this. This is pump B. So if we choose pump A or if we choose pump B, we will get the flow rate only 10 to the power of 2 gallon per minute. While the TDH, we can actually achieve only up to 60 feet. It does not meet our requirement. So in fact, what we want is we want the pumps operated at the ultimate capacities of 1200 gallon per minute at the total head of 80. So where do we want? We actually want 12 GPM. We actually want the head as largest as 80 feet. If we only have pump A and pump B, if the shops they can only supply either pump A or pump B, or if you buy A or B anyway, it will not give you a satisfactory result. In that case, what we can do, we can connect it two pumps in parallels or in a series. But in this case, we want a flow rate. We really want the larger flow rates. So in the larger flow rates, what you can do, so as I told you previously, if you want the larger flow rates, you have to connect the pumps in series. So if you want the larger flow rates, you have to connect the pumps in series. Now we have two choices, pump A or pump B. So if we want to choose the A plus A, maybe you can get like a 1200 gallons per minute, or you can choose B plus B. You may also get 1200 gallons per minute at the head 80 feet. But the thing is, these two pumps may not produce satisfactory efficiencies. For pumps A, if you really look into the pump curve, pump A, the efficiency is less than 60%. But for the pump B, if you choose pump B, the efficiency is something 65. Yes, 65. Okay. So here you can see like a pump B. If you choose pump B, the efficiency is greater than the pump A. So in this case, we will choose pump B, and then we connected B in series, because in series connections, only with the series connections, we will get the larger flow rates. Okay, so in this case, you just combine, you just install the pumps B, two pumps in parallel, B, like this. Okay, so if we connected pump B in parallel, what will happen to pump B? So if the pump B, there everything is the same. So if you connect two pumps in series, the flows will be double, but head remain the same. So if our curve is like this, so for the parallel, flow is double. This one is the flow rate. This one is the TDS. So flow is double, but head remain the same. So if we connect two pumps in series, so flow will be double. Flow rate is given in an x-axis. So flow will be double, like this. So here we can say like after combining two pumps, after joining two pumps with each other, So the pump curve will need to be modified to be something like this. This is the modified pump curves. So if we connected these two pumps in uh, parallel, not in series. And now if we have like a system head curve like this, so one pumps you only gets up to here, two pumps you gets up to here. But if you buy the bigger one, then calculate it. Okay, then just check um, the head again. So you find the positions where the pumps will be in operations. So this is how we modify the pump curve. So if we have like a two pumps or more than one pumps in operations. And what about the if we have like a two pumps connected in series like this? This one is called two pumps connected in series. So if we have like a two pumps connected in series, so the head can be increased, but flow rates can be the same, remain the same. So in this case, if we have like a pump curve like this, then we have two pumps connected in series. So these two pumps look exactly the same, has the same capacities. So the head will be double while the flow rates remain constant. So this is just the original curve, pump curve. And then this one is just double. So once we double this curve, we will get the curve for the two pumps connections in series. So this is how we select the pumps if we don't find any pumps match our requirement. Sometimes we may need to use two pumps connections, two pumps in series, and sometimes we apply two pumps in a parallel. Okay, so this is how we select the pumps, and we need to establish the curve. So this is the class which also explains what I have just finished. Now just come back to the pumps again. For the pumps, the impeller need to rotate it with the speed n, and the speed is actually has the relationships with the flow rates TDS and also the power. Q vary as n, TDS vary as the n square, and the power vary as n to the power of 3. So what does it mean? So what does it mean here? Q vary as n. N is the rotating speed, RPM. I mean the impeller rotating speed. Q vary as n. If we change the flow rates from flow rate 1 to a flow rate 2, the rotational speed. So if we change the rotational speed from N1 to N2, then the flow rates will be changing. So Q vary as N. So it gives this relationships to us so that we can make use of this. So if we change the rotational speed, then we'll get different flow rates accordingly. They actually vary. The flow rates actually vary as the end. And what about the TDH? TDH varies as n square. So this gives the relationships like a TDH1 divided by TDH2 is equal to N1 square divided by N2 square. And what about the power? Power in a first conditions, this also varies as n to the power of 3, n to the power of 3, n1, n to the power of 3, then n2 to the power of 3, like that. So these are the relationships we can draw from this information. The same as the diameters, sometimes we need to change the diameters of the impeller by removing some certain inches from the diameters. So Q varies as d to the power of 3. It means that Q1 divided by Q2 is equal to d1 square to the power of 3 divided by P1 to the power of 3, sorry, P2 to the power of 3. So this is another relationship. TDH 1 divided by TDH 2 is equal to D1 square divided by D2 square. And the last one is also same thing, power 1, power 2. So it's equal to D1 divided by D2. So it's proportional with each other. So these are the meaning of this relationship. So if you want to change the diameters of the impellers, so just check and find out what will be the TDH values and the powers requirement. Another thing which are involved in the pumping installations is the parameters called the net positive suction head. For the net positive suction head, so what does it really means? You have to think about how the water can actually get into the casing. Okay, water can actually get into the casing. So how the water can actually get into the pump's casing? So it's basically only by the atmospheric pressure, right? According to the figure A. So basically, the water can actually get into the water casing by the atmospheric pressure, which actually put the pressure on the suction reservoir. So basically, it's just the absolute pressure. But for the figure B, water which can actually get into the casing, so it's due to the absolute pressure here, because we open to the atmosphere. Okay, so it's just the absolute pressure plus the flooding pressure due to the flooded water. Okay, so pressure plus the pressure due to the flooded water. So it depends on the static suction head in this case. So if I ask you which one is better in terms of the pumping installation, so actually the type 2 or the figure B is better in terms of the installation, because it helps to push the water into there's the flood suction head, push the waters into the casings. So condition 2, all the arrangement, all the installations in a figure B is better in terms of the suctions. just a moment. I have another call. Why so many people trying to call me to? Okay. Uh, so water can actually get into the casing due to the absolute pressure, solely due to the absolute pressure in the case of the figure A installations. But for the figure B, there is pressure due to the flattened suction head here, which equal to the static suction. So basically, in a figure A, water has to be lifted from the suction reservoir and sent it to the discharge reservoir. But in a figure B, it is better. So the pressure entering uh, to the casing is normally called a positive suction head. The liquids must enter the center of the impellers under the pressure, usually the atmospheric pressure. But in case of the figure B installation, there is the flat suction head uh, additions to the atmospheric pressure. So this pressure is referred to the net positive suction head. In short, we call NPSH. Uh, for the pumps, there are two values of the NPSH. The first one is available, and then the second one is the required. The available depends on how we install the pumps. Uh, just like in the previous figure I show you, uh, figure A installation, so the figure B installation. So that one we normally call the NPSH available. But for the NPSH required, so this information will be provided by the pump manufacturer. So if you look back at the pump curve, you will find some information about the NPSH. Here is the NPSH curve showing uh, the curve with actually this should be a subscript R. It's basically refers to the required NPSH-R. NPSH-R is actually the required NPSH. So this NPSH is actually provided by the manufacturer. Okay, this required NPSH is provided by the manufacturer. It depends on the pumps itself, but the NPSH available depends on how we install the pumps. So uh, how does it matters if the NPSH is not uh, actually uh, high enough, or the NPSH available not comparable with the NPSH required? So what will happen? As I mentioned, the available NPSH normally depends on how we install the pumps, depends on the location, the size of the intake system. So uh, mostly depends on uh, 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 how we install the pumps and the intakes facilities. And this can be calculated by the engineer. So as we are engineers, so we have to determine the available NPSH. Anyway, the NPSH need to be positive. The NPSH need to be positives, and the NPSH needs to be greater than the required. Available NPSH needs to be greater than the required. So if the NPSH is smaller than the required, what will happen? Uh, there will be inside the casings during the operation. Uh, there will be a kind of uh, you have to imagine about the casings. Water entering to the casing uh, through the axial directions. So once these impellers rotated, the pressure is increased near the casings, near the wall of the casings. But at the center, the pressure generally drops. Okay, the pressures here, it's at the center, it's very low, but it increased near the casings wall whenever the impellers rotated. So this normally happens when the impellers rotate. The pressure here at the center, it's normally lower as compared to the pressure uh, near the casings wall. So what will happen? So if the pressure near the center, if the pressure here reduced to be lower than the vapor pressure, if the pressure at the center reduced to be lower or less than the vapor pressure, the liquids inside this chamber will become vaporized or change the status from the liquids to the vapors or the gas. So this gas or the vapor forms a bubbles. This bubble it actually forms due to the pressures of the liquids reach the vapor pressure. So under these conditions, there will be a bubble forms. So these bubble formations, we normally call this bubble we normally call the cavitation, okay, or the cavity formations. So when we operate the pumps, we need to prevent these phenomenon. We try to avoid the cavity formation. So how we can avoid the cavity formation? The NPSH must be greater than NPSH available must be greater than the NPSH required. And then how we can determine for the NPSH available. So NPSH available is equal to the absolute pressure plus or minus plus or minus. This can actually be plus or minus, positive or a negative. It depends on how we install the pumps. Actually, this can be a plus or minus. Then minus the head loss in the suction layers. Then minus the vapor pressure. So as the NPSH is the net positive suction head, we actually focus on the suction size. So we don't focus on the discharge side. This is our system. There is the pumping system installed here. This is the discharge reservoir. We only focus on the suction size. We don't focus on the discharge side whenever we calculated the net positive suction head. So net positive suction head is equal to absolute pressure plus or minus the static suction head. And here is the static suction head. The difference between the water levels and the pump's center line. And then the next one is the head loss. Whenever we determine the head loss, we only consider the head loss in the suction piping, not the entire piping system. Only in the suction piping, not in the discharge piping. So discharge piping is not included in the head loss determination according to this equation. Then absolute pressure, we have just to subtract this absolute pressure because we don't want the pressure reach the vapor pressure. That is why we have to avoid it. Water can actually vaporize. It doesn't the temperature doesn't have to reach the 100 degrees Celsius. Sometimes under the normal temperatures, room temperatures, the water can actually be vaporized. So if you observe the water bottles, you find drops of water stick it on the wall of the plastic bottles. That is because some of the water can actually vaporize, and then they distilled again becomes a drops of water. So this mechanism sometimes occur. Okay, so water becomes vaporized. Uh, it's not always uh, uh, happen under the boiling temperatures, normal temperatures. It can happen. So this is how we can determine the absolute pressure. But according to this arrangement, this is figure A. So if it's a figure A, the NPSH available, so you have to calculate it by taking the absolute pressure plus, minus, not plus, minus suction head minus loss minus vapor pressure for the A arrangement or the installation like this. But if we install the pumps like this is the pumps, and then this is the discharged reservoir. The center lines of the pumps is below the water levels in the suction reservoir like this. NPSH available will be equal to the absolute pressure plus HS minus loss minus uh, vapor pressure. So I like to emphasize here, if the liquid is below the center line, HS is negative. If the liquid level below the center line, H is negative. This one, you see the liquid levels here, center lines of the pumps is here. So here H is negative. So be careful while determining the NPSH available. So you have to compare the NPSH available with the required NPSH. You have to compare the NPSH available with the required NPSH, and then NPSH available need to be greater than the NPSH required uh, around at least 1 meters or above. So NPSH available needs to be bigger than the NPSH required, at least 1 meter. So this is the requirement for the design. So as the margins of safety. Cavitation. What is the cavitation? Cavitation is the phenomenon of the cavity formations or the collapse of the cavity. So it just form and then collapse. The bubble just form and collapse. So this happened during the pump's operation. Uh, uh, it only happened when the NPSH available is less than the NPSH required. Okay, it mostly happen when the NPSH available is less than the NPSH required. And then what will happen? A lot of noise is generated when the bubble is formed, when the cavity is formed and collapsed. Pumps is vibrating during working, so it's not good for the pumps in that case. So we have to avoid the cavity formation. Okay. This is the why we have to determine why we have to concerns about this kind of head called in net positive is suction head. Installations of the pump is also important. Okay, so these are the details about the cavitations. Okay, I think for the pumps issues we have now completed. Any things which I missed? Work power efficiency we already have talked about. Okay, just come back to this curve again. Talking about the total dynamic heat. The total dynamic heat you have to base on the fact that when we pumps the water from the lower reservoir to the upper reservoir, initially the static heat is like this. This is the static heat. But after pumping, what will happen to the water level? After pumping, what will happen to the water level? Water levels in the suction reservoir may decrease, while the water levels in the discharge reservoir might increase. So that if you measure the suction, the water level in between in the suction reservoir and the discharge reservoir, you will see a greater static heat at the end. So when we consider to buy the pumps, if there are too much water difference, you have to consider two conditions. So the first conditions, the initial condition, initially it was like this. So at the end, it get greater like this. So this is the initial static heat, and this is the static heat at the end of the operation. And if you combine this static heat with the major loss and minor loss, so you will get lines like this. So if you combine it with the initial static heat, you get this line. So if you combine the loss with the static heat at the end, you get this line. So the system is in fact starting from this line and end at this line. So we can say that the lines actually vary between these two parallel lines. So I mean the TDH varies in between these two lines. So when we consider the to choose the pumps, so we have to see the flow rates. The flow rates may vary slightly at the beginning and then at the end. So sometimes you may have to consider this range. So if as long as it's acceptable, it's okay. But if it's getting wider, so much different, so sometimes you may have to choose the other pumps. If you choose the small one, it may create the problems. You may have to choose the big one in some cases. Okay, so this is the problem related with these figures I like to explain. What else? Okay, varying speed. Sometimes we need to determine the pump specific speed. A pump specific speed, what is the pump specific speed? The pump specific speed is the speed at which the pumps will discharge just 1 unit of a flow under the 1 unit head at the maximum efficiency. So actually this factor is not very useful, so just to determine and compare with other pumps. So pump specific speed we can determine by using these relationships. The pump's specific speed is equal to the pump's rotative speed, normally expressed in terms of RPM, revolution per minute. Then the flow rates at the maximum efficiency divided by the total heat. So based on these three information, we can find out the pump specific speed accordingly. But as I mentioned, this value may not be very useful, but if just if you just want to compare various type of pump, comparison between pump specific speed of each pumps is okay. But in terms of the pumps selections, these may not be very useful. Okay, I think that is all for the pumps. So pumps combinations I have already talked about. Then we just move to the example. So before going into this example, I'd like to take a 5 minutes break. Uh, so uh, now it's almost 12 o'clock. So let's take a 5 minutes break to go to the toilets and having some water drink. เดี๋ยวแป๊บหนึ่งนะ เดี๋ยวผมกลับมา อันนี้นักศึกษายังอยู่ใช่ไหมฮะ
อยู่ครับ
อยู่นะโอเค เดี๋ยวแป๊บหนึ่งเดี๋ยวกลับมาขอเบรกไปห้องน้ำแป๊บหนึ่งนะครับ ฮัลโหล ฮัลโหลได้ยินปะฮัลโหลเอาเกมยาอ่อนอีกแล้วนะเที่ยงครึ่งอีกแล้วนะ
ใจเย็นครับ
โอเค so just continue นักศึกษายังอยู่ใช่ไหมฮะ
อยู่ครับ
okay let us begin with the this example related to the NPSH the problem associated with the NPSH is something like this the NPSH required for the pumps is 5.18 meters So this is the information provided by the manufacturer at the design flow rate. So if you're not sure, the pump curve may come different formats, but anyway, the curves must be provided by the manufacturer. It may comes with different formats, so sometimes it varies depending on the company. Anyway, for the NPSH, the problem is something like this. So this information we collected from the manufacturer, 5.18, the NPSH required. The water level is above the mean sea levels of 300 meters. So this refers to the water levels in the suction reservoir. For the NPSH, we don't pay attention on the discharge pipe and also the discharge reservoir. So just pay attention on the suction side. The total head loss in the pipeline is found to be 0.6 meter. Only in the suction lines, excluding the total head loss in the discharge side. Determine locations of this pump at the highest levels. So you have to find out the locations of the pumps at the highest levels. So what does it mean? It means that you have to okay. So the question is like this. This is the suction reservoir and this is the pumping system
สกรีนเลยครับ
ฮะ
อาจารย์
เหร
ยัง
อ
ไม่แชร์สกรีนเลย
อ๋อ
ไม่เห็นจอครับผม
ครับแป๊บหนึ่งokay. So this is our system and then this questions is asking about this level, how much higher, the highest levels that we can install the pumps, the highest levels, suction head. What will be the highest levels for the suction head? Okay, so this question is asking for the suction head. So it can be any height as long as it's still as long as the NPSH available is greater than the NPSH required. NPSH required, okay? So it can be at any level as long as the NPSH available is greater than the NPSH required. That is why this question is asking for the locations of the pumps at the highest levels. So you have to think in mind. You have to keep in mind it can be at any level as long as the NPSH available is greater than the NPSH required. In this question, then there is no any information about the safety factor, so you can ignore it, or you can include the safety factor. It doesn't matter. So safety factor, like I'm talking about the safety factors between the NPSH available and the NPSH required. So it should be at least greater than 1. But according to this example, they don't mention about the safety factor. Okay, so this is the question. The objectives is you have to find out the suction head. If you install it like this, it won't be the problems. Okay, this is okay. That there will not be any problems. But if it's like this, so you have to be careful how much higher you can install this pump. Okay, the problem is we have to find out the NPSH. NPSH is equal to absolute pressure plus or minus the static suction head, and then minus head loss, and then minus the vapor pressure. The question is asking about the suction head. So this amount you have to determine. Okay, and asking about the highest, it means that this the installation like this needs to be minus only. You cannot use the positive. Positive means the installation like this. Okay, so this is the equation. So just substitute each parameters into this equation and find out. You can simply do this way. Our NPSH available should be greater than 5.18. So we put it here. You can make like a 4, or you can make like a sorry, you can make like a 6. It depends on your assumption. Then find out the absolute pressure, find out the loss, and then find out the vapor pressure. But in order to find out each individual parameters, you have to look into each of this. For the absolute pressure normally vary depending on the elevation. This is the relationship showing the how we can determine the absolute pressure based on the elevation. So if the elevation is 300 meters above the mean sea levels, so in terms of the water column's height, so it should be like a 10.01 meters. Remember that this is the at the normal temperature. This is at the normal temperatures. Sorry, this is at 4 degrees Celsius. This is at 4 degrees Celsius, not any other temperature. But our water temperature is 30. But this equation is applicable only at 4 degrees Celsius. So if we are, if our water temperature is not 4 degrees Celsius, so we have to adjust the value that we obtained from this calculation. As 4 degrees Celsius, why the 4 degrees Celsius is important? If you look at the information that I gave you, whenever we talk about the density or any other factor, so see at 4 degrees Celsius, specific gravity is equal to 1, exactly 1. The higher temperature will be the lower specific gravity, and then lower, less than 4 degrees Celsius, the specific gravity is also less than 1. So 4 is critical temperatures. It's important temperatures for the water. So it's like a maximum is the temperature where the specific gravity reached the maximum, which is also equal to 1, as we all know that, not any other temperature. That is why most of the equation applicable only at 4 degrees Celsius. Like the vapor pressure shown in this table. This table also shows the temperature at 4 degrees Celsius. The information is with respect to the temperatures at 4 degrees Celsius, but whenever we want to apply this information at various temperatures, we have to correct the value. So how we can collect the value? How we can collect the value? So for the 30 degrees Celsius, so you have to look at the specific gravity. So 30 degrees Celsius, specific gravity, it's 0.9957. So that you have to correct this value. So 10.01 divided by specific gravity, then we get the vapor pressure at 30 degrees Celsius. The absolute pressure at the 30 degrees Celsius. Similar to the vapor pressure we have obtained it from the table at 30 degrees Celsius. So this is 30 degrees Celsius. The specific gravity, vapor pressure measured in terms of meters of water. So it's 0.43. So for this one, we also have to correct this value because if you really look at the table title, specific gravities and the vapor pressure at various temperature. The vapor pressure is expressed in terms of millibar and water column's height at 4 degrees Celsius. So whatever the value showing in this column is expressed in terms of is with respect to 4 degrees Celsius. The unit is meter, not with respect to at any temperature. So if you want to use, you have to correct this value, okay, by dividing the specific gravities. But it's slightly different because the specific gravities at this temperature is 0.9957. So 0.43 remain the same even we correct it. So just allocate the number, just substitute this number into this equation. Then we get like we can locate the pump at 3.84 meters above the water levels in the suction reservoir, and that would be the maximum height that we can install this pump under these conditions. Okay, so this is the NPSH issues. Whenever we install the pumps, especially the centrifugal pumps, we need to be aware of the NPSH available. Otherwise, if you do not follow the guideline, if you don't follow if you don't maintain the NPSH available greater than the NPSH required, you will end up with the cavity formation, and finally the pumps will be damaged if we still keep on operation that pumps with the cavity formations. Okay, so this is about the NPSH required. Then we just come back to the assignment. So assignments I have given to you this morning, there were about 3 pages. So the first 2 questions is actually related to the storage volumes determinations. Hopefully you can find the answer. Then just come to the question number 3. Question number 3 onward are related to the pumping system. For example, the question number 3, this is probably the simplest one. A centrifugal pump is operating at the speed of 1200 RPM and the discharge 2.5 cubic meters per minute. The total heat of 120 kilopascal is measured on a pressure gauge located at the discharge pi. So Then the power required is a 7 kilowatt. This is the power required, from the pumps, not the power output, okay, not the power from the systems. Calculate the pump's efficiencies and the discharge head and power if the pump speed is changed to 1800 RPM. So the first question, so how we can solve the problems. So you have to determine the pump's efficiencies. So pump's efficiency, remember that the pump's efficiency is equal to power output divided by power input into 100. Then you will find the pump's efficiency. And this is the power required is 7 kilowatt. 7 kilowatt in this context refers to the power input. So you have to find the power output in order to determine the pump's efficiency. So what is the power output? P is equal to gamma QH, right? The total head is given in terms of the kilopascal, not in terms of water column's height meters. The flow rate is 2.5 cubic meters per minute. So can you just find out the power right now? What is the power output? You already have the information. Gamma QH. Can you just find out quickly? ได้เท่าไหร่ฮะ power output. The total head is already given. The flow rate is already given. Can you just find out the power? You need calculator. All the engineering students are required to be with the calculators. ได้เท่าไหร่ครับ มีใครอยู่ในนี้มั้ง NP นี่คือใคร NP ไปไหนละ ณัฐพัฒน์อยู่ไหมครับ ณัฐพัฒน์อยู่ไหมฮะ GP นี่ใครเนี่ย กันพิเศษอยู่ไหมครับ
ครับกำลังดูอยู่ครับผม
ได้เท่าไหร่ฮะ simple calculation นะฮะ PP พิชพัฒน์ใช่ไหม พิชพัฒน์นี่ผู้ชายหรือผู้หญิงอะ
ผู้หญิงค่ะอาจารย์
อ๋อเหรอชื่อมันเป็นได้ทั้งผู้ชายผู้หญิง ลักษิกานี่ผู้หญิงแน่นอนใช่ไหม
ค่ะอาจารย์
ได้เท่าไหร่ ได้เท่าไหร่ครับ ได้เท่าไหร่ power มีใครได้ตัวเลขนี้แล้วบ้าง
ไอ head loss เราต้องเปลี่ยนอะไรมันหน่อยป่ะครับอาจารย์หรือว่าใช้ตัว
ใช่
120K
ก็แล้วแต่ทุกอย่างต้องอยู่ในหน่วย SI มีใครได้คำตอบแล้วบ้าง ข้อนี้เป็นข้อที่ง่ายที่สุดเลยนะ ในการบ้าน ณภัสกรอยู่ไหมครับเนี่ยณภั
อยู่
สก
ค่ะ
ร
เดี๋ยว
อ่ะ
สักค
ได้
รู่
เท่าไหร่
นะคะกำลังดูอยู่เดี๋ยวแป๊บหนึ่งนะคะ
ตอนนี้เป็นหน้าสกรีนใช่ไหมครับ มีใครตอบได้มั้งได้เท่าไหร่ฮะ simple มากเลยนะอันนี้เนี่ย
42อะครับ
หน่วยคืออะไรครับ หน่วยคืออะไรฮะ
อาจารย์ขอดูหน้าโจทย์อีกรอบได้ไหมครับ
อ่ะ ได้เท่าไหร่
ได้42ครับหรือเปล่า
อะไรนะ ได้เท่าไหร่นะ42%เหรอ หน่วยเป็นอะไรฮะ เปอร์เซ็นต์หรือว่าเป็นอะไร มีใครอยู่ในนี้มั่ง อันนี้เป็นคำถามที่ง่ายสุดเลยนะเนี่ย ได้เท่าไหร่ครับ JP นี่ใครเนี่ย จุลจิตอยู่ไหมฮะ จุลจิตอยู่ไหมครับ มีใครได้คำตอบแล้วบ้าง
1 หรือเปล่าคะอาจารย์
1 อะไรฮะ หน่วยอะไร หน่วยเป็นอะไร
อาจารย์ผมต้องเปลี่ยน
หรือเปล่าคะอาจารย์
อะไรนะครับ อะไรบ้างนะ เมื่อกี้ผมไม่ได้ยิน
หน่วยเป็น watts หรือเปล่าคะอาจารย์
หน่วยเป็นวัตต์ฮะ หน่วยเป็นวัตต์where is it the power can be determined from this relationship, so it's equal to gamma q TDH. The units of the power it's given as watt, kilowatt. Q is given as cubic meters per second. Then the TDH is given as meter. So the unit is kilowatts because the specific weight of the liquid pumps is given as kilonewton. So if you are using Newton, so the power, the unit should be a watt. So in this question, what I'm going gonna ask you is I'd like you determine the power output based on the operational condition like this. The total heat the unit is meters, not kilopascal. มีใครได้คำตอบแล้วบ้าง ใครได้คำตอบเป็นคนแรกนี่เดี๋ยวจะมีคะแนนให้ ตัวเลขวนอยู่ไม่กี่ตัวเองเนี่ย WJ มิสเตอร์ WJ วัชรพลใช่ไหมอยู่ไหมครับ ได้เท่าไหร่ วัชรพลวัชรพลฮะ
ได้ 42%บ้างอาจารย์
42%ไม่ถูก เมื่อกี้ใครจะพูดเนี่ย สิทธิพลเหรอนะฮะ สิทธิพลได้เท่าไหร่
ก็พูดไปเมื่อกี้ครับ
40เหรอเมื่อกี้คุณคือสิทธิพลใช่ไหมอันนี้คือใครเอ่ย ฮวนได้เท่าไหร่เอ่ย so what is the power output you have got it from the calculation
หนูได้71ค่ะ
71 that is the correct answer so can you just explain how did you achieve how did you get this number 71เนี่ยเป็นคำตอบที่ถูกนะได้ยังไงคุณลองอธิบายมาสิยังไง
120คูณ 2.5 แล้วก็เปลี่ยนหน่วยเป็นมินิก็เปลี่ยนหน่วยเป็นไซเคิล
ยังไงต่อเปลี่ยนยังไง
หาร60ใช่ไหมคะ
แล้วยังไงต่อ
แล้วก็ไปหาร p in แล้วก็คูณ100
หารอะไรนะ
power require ค่ะ
power require คูณ100 you get the correct answers but you still misunderstand something h is given as the meters นะ h นี่มันเป็นเมตรนะไม่ใช่กิโลพาสคาล the thing is heat is equal to P divided by gamma so in fact power is equal to gamma Q H right so H is given as 120 kilopascal so this one is actually P so you have to divide it by gamma and Q is okay this one so this one you have to divide it by gamma and then there is another gamma here so this is the power so this one is gamma this one is gamma so these two get cancelled then we only get the power equal to 5 kilowatt that's all for the power output then if you take 5 divided by 7 into 100 so you will finally get like a 71 จุดอะไรนะ 71 something percent this is the answers to the question A and what about the question B the total discharge heat and power if the pump speed is changed to 1800 rpm so how we can get the discharge do you still remember a Q vary as n Q1 divided by Q2 it's equal to N1 divided by N2 So initially, we have like a 1200 RPM. Then we increased the speed to 18 RPM, so that the flow rates we get from the at the 1200 RPM, it's 2.5 cubic meters per minute. Then you can find out the flow rate if we increased the rotational speed to 1800 RPM. The same as the TDH power. TDH vary as n square, and then the power vary as n to the power of 3. So you can find out the new heat and the new power. So when we operate the pump at the speed 1800 RPM. Okay, so this is the first question. But the first question related to the pumps, and then question number 4 is about the NPSH. Question number 6 is interesting. You have to develop the you have to establish the HQ curve. It's a big question, and there is a pump curve provided by the manufacturer. So what you really need to do is, in this question, you have to establish the pump curve. One pumps in operation, you get something like this. So if you have 2 pumps connected in series, you will get something like this. If you have 2 pumps connected in parallel, you will get something like this. And then, based on the information here, you are supposed to get like the HQ curve like this. So at each curve, you get the point where the pumps will be operated. So this information is the information you prepare to determine this curve, and this curve. But this information, you take it and prepare this curve. Okay, but the only thing is, friction loss, you have to use the Parsons-Williams equation. The Parsons-Williams equation, it's based on the flow rate divided by 0.278 CD to the power of 2.63 to the power of 1 over 0.54 into L. In fact, it's loss divided by L is equal to this amount. Then we take L to the other, this is another size. So just substitute Q at various flow rates and in order to get the loss. C is already given. C is already given. So substitute it into here. D, this one is D, diameter. Sorry, D is this one. So just find out the curve like this, then only this you will be able to answer the question. So question number, this question is interesting. It's a big question, question number 6. Sometimes I also ask calculate the annual billing, power billing for a pumping rate like this, the unit cost power is 5 cents per kilowatts. Assumes C it's 100% combined, and the pumps and motor efficiency is 78%. So sometimes you have to determine the annual power bill. So in order to determine the annual power bill, so here it gives like a kilowatt hour, okay? Kilowatt hour is the power. So for this question, question number 5, at least you have to find out the power. First, you have to find out the power. Remember that the power is equal to gamma QH. Then you have to find the TDH. TDH is equal to static heat plus major loss and the minor loss. Okay. So once you know the static heat, then multiply by the flow rate. The flow rate is already given. This one is the flow rate. And then at the end, you find out the power. So this is the way we determine the annual power billing. So if the pump is operated 24 hours every day, 365 days a year, it doesn't matter because this one is per hours. So how many hours in a year, you just multiply. Okay, this one is also per kilowatts. Okay, this one is also kilowatts. So based on this information, I think you can find the annual power bill. So it's really straightforward, right, to determine the annual power bill. But you really need to determine how many kilowatts these pumps required. There are not many questions, just 8 questions totally, but many are quite a big question, so you may have to spend some time to complete it. Okay. Do you have any question related to the pumping system? มีคำถามไหมครับ You've got a new assignments today.
อาจารย์ครับ
ครับ
ผมขอถามครับว่าอาจารย์มีเฉลยของการบ้านครั้งที่แล้วไหมครับ
มีแต่ว่าเดี๋ยวค่อยอธิบายพร้อมกันวันนี้ยังไม่จะแต่ว่าจะไม่ได้แจก
โอเคครับ
เดี๋ยวอาทิตย์หน้าค่อยว่ากัน
ครับแล้วสรุปสอบแลบวันที่เท่าไหร่ครับอาจารย์4
ห้า
หรือ5 ใช่ไหม5มันตรงกับวันศุกร์นะครับ
วันศุกร์
ตรง
ครั
กับบ วันศุกร์ตอนเย็น
อ๋อครับผม
ตอนเย็น
แล้วสอบถึงแลบที่4ใช่ไหมครับ
แลบ5แลบวันนี้
โอเคครับ
วันนี้มีอีกแลบหนึ่ง
ครับผม
แลบของเรา
ใช่ครับ
schedule lab ของเรามันวันที่อะไรนะในตารางอ่ะ
เหมือนจะ
ไม่ได้
ปที่ห้า
อาจารย์
ตารางยังไม่ออกเลยครับ
แลบนะเฉพาะแลบนะ
แล้วครับ แต่ว่าของ lab อะไม่ได้ออก เขาบอกว่า to be assigned
อ๋อใช่
น่าจะนอก
แลบ
น่าจะนอกตารางอะครับผม
แลบนัดกันเอง เดี๋ยวก่อนดูใน MS Team เดี๋ยวนะ ผมลงไว้ตอนแรกผมลงไว้อยู่แต่ว่า ผมไม่มั่นใจว่าวันไหน อาจจะเปลี่ยนเป็นขอเปลี่ยนเป็นวันที่5ก็แล้วกันฮะตอนเย็นสัก4 โมงครึ่งเป็นต้นไปนี่นี่ไง5 ตอนเย็น March 5 นะฮะ March 5th 2021 สัก4 โมงครึ่งก็แล้วกันครับ วันที่5
อาจารย์ครับกี่ชั่วโมงคะอาจารย์
ชั่วโมงครึ่งถึงไม่เกิน2 ชั่วโมง
ก็คือ4 โมงถึง5 โมงครึ่งใช่ไหมคะอาจารย์
4 ครึ่งถึง6 โมงหรือ6 โมงครึ่งนี่แหละผมยังไม่ได้คิดว่ามันจะ ชั่วโมงครึ่งหรือว่า2 ชั่วโมงยังไม่แน่ใจ แต่ว่าเบื้องต้นเนี่ยชั่วโมงครึ่งแน่ๆครับ
อาจารย์ค่ะแล้วข้อสอบเป็นเขียน short answer หรือเขียนยาวๆ หรือว่าเป็น
บอกไม่ได้ อันนี้
อ๋อ
เป็นความลับฮะยังบอกไม่ได้ แต่ว่าสิ่งที่นักศึกษาเตรียมตัวก็คือ